right, so here we are. I'm going to continue on with lesson 3 in chapter 7 when we were dealing with rational exponents. So we've had exponents that were fractions, and we may have that again, but we're going to add to that. We're going to look at some equations where exponents are variables. So in order to solve those, we are going to have to use all the exponent rules that we know, and including this new one right here, this power of equality. If we have an equal sign, so two things that are equal, and we have a base that's positive, a positive base, and not equal to 1, obviously, because 1 to any power is going to be 1. So if we have an equation with two powers, if I raise both of those to another power, as long as I raise them to the same power, they're going to continue to be equal. Okay, and you're probably asking me, why would I do that? Well, let me show you. Okay, so right here are some equations. In this equation A, we have 4 to a y power, so some unknown power, which is what we're trying to find out, and it equals 1024. Okay, so what we have to do, we know that they're equal, so 1024 has got to be 4 to some power. So realistically, it comes down to you're going to figure out how many times 4 goes into 1024. So I was showing work. I know that 4 cubed is 64. 4 to the 4th then would be 64 times 4, which is 256. And 4 to the 5th then would be 1024. Double check my math, and I am correct. So 1024 is really 4 to the 5th, which means that y, exponent y, equals 5. Now that was a pretty straightforward question. It's just rewriting 1024 as a power with a base of 4. But take a look at B. Okay, in exercise B here, we have 36 to, and actually that's a binomial. There are 2 terms in that exponent. Okay, don't panic. And then we have 216. So the trick of this is we are going to have to write both of those to the same base, meaning same number to a power. So I'm going to start with 36. 36, hopefully most of you know, is 6 squared. And after yesterday, or after our last half of this lesson, I'm hopeful that most of you can identify 216 as 6 to the 3rd power. So I'm going to rewrite them. I'm going to, instead of writing 36, I'm going to write 6 squared to the x plus 2 power, and 216 is 6 cubed. Okay, so now I at least have both the same base of 6. So if we look at this, the second one is fine. I'm going to leave that one alone. But that first one, when we raise a power to a power, we multiply exponents. Now, when we multiply, we have to actually distribute this to both of those. So it becomes 6 to the 2x plus 4 exponent. And as long as they're both a base of 6 to a power, and they're equal, those powers have to be equal. In other words, your 2x plus 4 must equal 3. Now we just have a 2-step equation we have to solve. So subtract 4. So 2x equals -1, and divide by 2. And x is, running out of room, -1/2, which we know yesterday is possible. All right? If I put that in there, that'd be -1/2, so that'd be 3/2, and so on and so forth. And I could do 36 to the 3/2 equals 216, which would mean I'd take the square root of 36, and then I'd cube it, and that'd be 6 cubed, which is 216. We are correct. Okay? Now, remember that because I can raise both sides of an equal sign to the same power and keep it equal, that's what we're going to use in this word problem down here. All right, take a look. We have the population of a specific species of insect is modeled by this equation. P equals 30 times D to the 2/5 power, where P is the population of the colony and D is the number of days after it's formed. How many days will the colony have a population? After how many days will they have a population of 300? So 300 is our new P, and we are solving for how many days. So I'm going to take that equation, which is P equals 30D to the 2/5 power. Okay, and actually P is 300. So when will it equal 300? Well, the first thing I'm going to do is divide by 30. And I get D to the 2/5 equals, cancel that out, and it's going to be 10. And now what I have to do here is I want to get rid of this 2/5. So what I'm going to do is I'm going to take both of these to the 5/2 power. Because when I do that, these cancel and just gives me D. So I have 10 to the 5/2 power. All right, well, that is the square root of 10 to the 5th power. And if I'm doing my math, that would be, so D equals the square root of 10 times 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 the square root of 10. I know that this is 10, that this is 10, and this is the square root of 10. So 100 times the square root of 10, which is, and I can use my calculator here, how many days? About 316 days. And it's about, because I'm rounding, so I should put my squiggly lines there, my approximation sign. All right, let's try another one like that. Population of a culture begins with 40 bacteria, doubles every 8 hours, and can be modeled by this equation, where T is time in hours, and P is population. Find T if P is 20,480. Okay, so I got 20,480 equals 40 times 2 to the T over 8. Alrighty, well, let's see, we're going to divide by 40. That's the coefficient. 20,480 divided by 40 gives me 512. Equals 2 to the T over 8 power. Now, that is a hideous exponent. So I want to get rid of the fraction. So what I'm going to do is I'm going to raise both sides to the 8th power. I'm not actually going to do that, so just breathe for a second. But I did that so I can cancel this out. I got 2 to the T equals 512 to the 8th. I said 12, wrote 18 to the 8th power. Now, why didn't I raise 512 to the 8th power? Well, 1, it's going to be just a ginormous number. And 2, because I have a sneaking suspicion that I can write 512 as a power of 2. Okay, 512 is a power of 2. I'm going to tell you that. I had to do some work. I believe it is 2 to the, 9th power. So this is 2 to the 9th to the 8th power equals 2 to the T. Well, when I raise the power to a power, 2 to the 72nd power. So T is 72 hours. Now, just think about that for a second. In 72 hours, in 3 days, your bacteria goes from 40 to 20,000. That's crazy. All right. Your next problem is actually on the bottom of this page, your page, but I have to flip mine over. So we're doing the last one. Here's one a little bit different. Our variable is not our exponent in this one. So I wanted to do one more like this. It says the radius of the nucleus of an atom has mass number A is R equals 1.2 A, area to the 1/3 femtometers, fun word. Find A if R is 3.6 femtometers. So I'm going to take that equation and make it 3.6 equals 1.2 A to the 1/3 power. Just substituting that in. Now let us solve for A. First thing I'm going to do is divide by that coefficient, so 1.2, which is nice because it comes out so pretty. So A to the 1/3 power equals 3. Now, I want to know what A is, so I got to get rid of that exponent. I can get rid of that exponent by raising both of them to the 3rd power, because when I raise that to the 3rd power, I multiply 1/3 times 3, and that goes to 1. So A equals 3 to the 3rd power, and hopefully we know that, 27, and my label is femtometers, and I have no idea what that is, squared. 27 femtometers squared is the area. It's got to be a very, very, very tiny, tiny unit, because we're talking about the nucleus of an atom. Okay, so very small. All right, this is where we're at. Your assignment is, oh shoot, I should have that with me. I've got another worksheet for you, or another copy for you. It is going to be right here. It's on the gold paper. I copied it out of the book for you again because I'm a super cool teacher. 7.3, page 411 this time, and you're going to be doing a handful of problems, 48 through 45, 45 through 48, excuse me, 52 through 58, 98 through 104. There's only 18 questions, but there are 3 word problems, so do the best that you can, and I will be here for questions. You can come see me tomorrow morning if you need to. All right, good luck.